Good afternoon.
Hello guys, nice to see you. How are you doing?
Good afternoon.
Very good.
Well, that's good.
Good afternoon.
Hi, good afternoon. So last week we were discussing waves in general and mostly focusing on wave on the string, which is which type of wave is wave on the string, by the way?
Transverse.
Transverse, yes. Today we start considering sound waves, which are longitudinal, and we will try to find the relationship between the displacement of some elements of gas when a sound wave is moving in this environment and some change in pressure. So let's see which equations describe change in pressure, how it's different from the equation which describes the displacement as a function of position and time, which like wave function. But in this case, we will highlight that this wave function will describe not displacement along axis x, but along axis, not along axis y, but along axis x, along the same direction as the propagation of the wave. Yes, sure.
Is fundamental frequency for one wavelength?
Can you repeat your question? What do you?
Is fundamental frequency for one wavelength?
I mean, if there is some wave with certain wavelengths, that wavelength correspond to a certain frequency. That if that is monochromatic wave, means there are no other waves which are similar but a bit longer or shorter wavelengths. Then we will have some distribution of wavelengths in this package, and then will be different set of frequencies. But if we have monochromatic wave with known wavelengths, then yes, there is corresponding single value for frequency. If I understood the question.
Okay, thank you.
Okay, and another subtopic we will consider today, we will try to derive equation for the speed of sound. So those are our goals for today, and let us change the screen to the slides. Let's hope it works. It somehow always creates. Okay, now it works. It's very good. So, a good model for considering sound waves is some cylinder with a piston. So this piston can move back and forth. And it will create some repeating pattern of high and low pressure regions. So this region will stand for high pressure. So in between we will have low pressure, and then again high pressure. So if we now consider pressure versus position, for instance. So we will get something like small pressure, then high pressure, small, high, and so on. So these regions with high pressure are called compression regions, and regions with low pressure, they are called rarefaction regions. So now,
excuse me, please. How are they called regions with low pressure? Could you repeat,
rarefaction,
please?
Rarefaction. Yeah.
Oh, thank you very much.
You're welcome. Rarefaction region. So, if we consider some small volume of gas inside this cylinder, then it will also move as similar as the piston, left and right. So the motion will happen in the same direction as the propagation of the sound wave in this cylinder along axis X, and that's definition of the longitudinal wave. And displacement can be represented by the wave function, let's say as a function of position, time, position and time. However, in this case, highlight this difference. We don't consider displacement along axis Y as we did previously. So we will have the same equation with the same position and time dependence, but this displacement instead of y-axis will happen in along x-axis. So we can write for this displacement as a function of position and time that is equal, we know it from like previous discussions, that is as maximum, we need to have some amplitude displacement from equilibrium condition, and this cosine kx minus omega t. So this we may have or may not have this initial phase constant p, but now it's not so important. So our first goal is to find the relationship for pressure, like excessive pressure or change in pressure, as a function of position and time, also similar to displacement. Actually, we want to find the relationship between the displacement and pressure. For this purpose, let us consider some volume of gas. Let's say this is our volume of gas. Then, because of any reason, any arbitrary reason, suddenly from the left side, there was some excessive pressure, and this volume of gas started to move under effect of that excessive pressure to the right. So because of compression of gas, displacement of the left edge of this gas volume, let's call it S1, will be larger than the displacement of the right edge. Let's call this displacement S2. So if we consider now delta S, difference in displacement of the left and right side of this considered cylinder, S1 minus S2. It will not be equal to 0 because we have some compression, some reduction of the volume. So this delta V can be considered as delta S, difference in the displacement, times A, which is area, cross-section area of this cylinder, which we consider in this example. So that is change in the volume. Now we can write that there is a relationship between change in pressure. So that's capital P. We will have also small p later for momentum. Is equal to minus B times delta V divided by V initial. So there is a simple relationship between change of volume with respect to initial volume of a gas via some coefficient called bulk modulus and defines properties of the gas. We can calculate change in the pressure. So we already know that this in numerator delta V is equal to delta S times A. As for V initial, its initial volume, then we consider some length of this cylinder, which is delta X. So initial volume V initial can be expressed as delta X times A, area, cross-section area of this cylinder with gas. So now let us substitute for delta V and VI. So that will be minus B times delta S times A divided by delta X times A. Cancel A from both parts. And we end up with minus B times delta S divided by delta X. Assuming some limit when delta X approaches to 0, we will get to the derivative, first derivative of displacement S over X position, but since our displacement is a function of X and time, like two independent variables, that will be partial derivative. So that will be minus B ds over dx. So here we can put x and t to highlight that this is partial derivative over position x, assuming t as some constant. Okay, so now we have this relationship which gives us change in the pressure, and we relates with the first derivative of the displacement function, like wave function of the displacement of elements of gas over x, position x, via this bulk modulus constant. So now let us substitute this equation for displacement and take this partial derivative in order to get the final expression for the change in pressure. So let us go to another slide. So here we can write that delta P is equal to minus B, this partial derivative, d over dx. And here our function for S versus X and T. So that was S maximum times cosinus kx minus omega e. So if we take derivative, we will get derivative of cosinus will be minus sinus, and this minus in front of b will cancel out. Then we will take derivative of the argument of the cosinus. T is considered as constant, so it will be omega t is 0 derivative. And here we will get k, wave number. So no, we don't have minus anymore. It will be B times S maximum times K times cosinus, sorry, not cosinus, sinus times sinus kx minus omega e. So this part stands for maximum change in pressure. We will come back a bit later to this point when we consider in more details maximum change of pressure. But we see that there is a difference between expressions for displacement and change in pressure. So there's cosine and sinus. Means that there is some phase shift in 90 degrees between pressure and displacement. So if we represent it graphically, say we have displacement S and pressure. So displacement, it's cosinus, so it starts from 0, goes like maximum, goes to minimum, comes back. And if we consider these extreme points, we will get, when there is minimum displacement, we will get maximum this change in pressure, and minimum change in pressure from equilibrium condition when we have maximum displacement. So there is this phase shift between displacement and change in pressure, and that we see it is coming from taking derivative, since there is a relationship between the change in pressure and first derivative over x of this wave function. We go from cosinus to sinus. Okay, now let us focus on the speed of sound. For this purpose, we also consider some cylinder with a piston and some volume of gas. So initially, this system stays in equilibrium condition. Means from this side, changed. On this side, we have some force, which is pressure times area times unit vector I. Let's say this is our axis x. And here will be minus because it's in opposite direction. Since it stays in equilibrium condition, then piston should provide the same force, but in opposite direction to the force exerted on the right side of this gas element. So that will be P times A times I. However, something happens and there is some excessive pressure from the side of the piston. Let's consider some delta P. Obviously, that will push this system out of equilibrium condition. So this is our cylinder. Now, if we consider this initial position of the left side of the piston, then because of excessive pressure, it moved to the right and kind of pushing this gas also to the right. However, we need to specify one condition for our derivation here. So let's say this displacement will be Vx times delta t. Vx is the speed of the piston, which is driven by this excessive pressure. So here we have P times delta P times A times unit vector I. If we consider very small volume of gas, then it's also possible to assume that gas will move with the same speed as piston is pushing it to the right. However, now let us consider what will be the initial volume which we deal with in this imaginary experiment. So this distance from the left to the right side of the considered gas should be equal to V times delta T. So this delta T is time interval between these two conditions, equilibrium condition, and then after some time interval delta T before, after exerting additional excessive force on the piston, which pushes the air to the right. And we pick up the width, like the or length of this gas cylinder, that way that it is equal to speed of sound in this gas times this time interval delta T. So why we do this? Because we want to be sure that at the right side from this right edge of the gas cylinder, we will have undisturbed gas. So it will be the same minus P times A times I. Why it happens? Because when we create some mechanical disturbance with the piston in this gas volume, this mechanical disturbance should propagate, move along the cylinder in the gas, and it can move with the maximum speed, which is defined by speed of sound. So that means that in time interval delta t, when there is some displacement of this piston from the left side, Vx times delta t, the disturbance will only reach the right edge of this cylinder because it can move with speed of sound, and maximum distance it can move is v, speed of sound, times the same time interval delta t. So in that case, we will have some excessive pressure at the piston, which moves, is displaced by Vx delta t, and over this time interval, sound had enough time to travel along all our considered volume of gas and just reached the right side of the gas in our cylinder, and everything what is further is not disturbed. We have the same pressure as under equilibrium condition. So now, if we have some excessive pressure, it will result in some net force from the side of cylinder. Like net force, it's a difference between the force exerted from the cylinder and the force exerted from the rest of the gas further from the right side of the considered gas cylinder. So we can write that this excessive pressure will result in some impulse of force, which is equal to change in linear momentum, P. So this is small p, not capital. We remember from considering the dynamics that impulse of force is equal to the net force times time interval delta t. That will be equal to area of cross section of the cylinder times excessive pressure delta P times delta T. And we can multiply it by unit vector to show that it's along axis X. Now we remember from previous slide that, so this is capital, this is excessive pressure, that this excessive pressure can be expressed in terms of bulk modulus and change in volume, and in like ratio of change in volume and to the initial volume. So minus B. So what should we put instead of delta V, change in volume? Any ideas?
A multiplied by Vx multiplied by delta T?
Yes, that's right. But we also need to put minus here because that's delta V is negative, it's compressed. So
right.
Yeah, Vx times A times delta T. That is good. So we have it here. Now we have initial volume, which will be defined by V times delta T times A. So V times A times delta T. And V stands for speed of sound. So these two minuses will cancel each other. Then we can cancel these guys. So it will be B times Vx divided by V. Now, if we substitute this expression instead of delta P here, we get further impulse that it's equal to A times B times Vx divided by V times delta T, and that everything multiplied by unit vector I. So now we have left side of this equation. Let us write the expression for the right side. So that is change in linear momentum. We know that we can write it like this. It will be m times delta v. M is mass of the gas. And delta v is change of the speed. So in this case, mass of the gas, it can be given in terms of volume, initial volume times density. So we have rho times initial volume. Then we have different like delta V, and delta V will be Vx times I unit vector minus 0. Because initially we had equilibrium condition, this gas was not moving anywhere, and after excessive pressure was appeared, piston started to move with speed Vx. Assuming very small volume of the gas, we can claim that it also moves with the same speed as the piston. So also substituting Vi with V times A times delta T, we eventually will get the following expression. So rho times V times Vx times A times delta T. So didn't forget anything. V A delta T Vx, no. And that will be multiplied by unit vector I. So now we have left side. So this is a left side and right side. We can equate magnitudes of these vectors and express speed of sound from it. Let us do it on the next slide. So in the left side, we can write A times B times Vx divided by V times delta T. That is equal to rho times V times Vx times A times delta T. So this and this and this we cancel out. Vx we cancel out. And as a result, we get that speed of sound is equal to square root of bulk modulus B divided by rho, which is density of the gas. So that is the equation which we wanted to derive, speed of sound. We can compare this, for instance, to the speed of wave on a string that was square root tension divided by linear density. Similar configuration. In the numerator, we have some elastic properties of the medium. And in the denominator, we have some inertial properties, means density either per volume or per unit length. So that is common for all speed of all waves in different environments, not only for gases, but also for solid state materials. Just instead of this bulk modulus will be just different parameter, which will also describe elastic properties of the material. Another thing which should be highlighted, that speed of sound depends on temperature, and for sound propagesting in atmosphere, we can write the following equation, some empirical form of equations. 331 times square root of unity plus temperature in, let's write like this maybe. That will be confused with time. So let's write T, but it's in degrees Celsius, divided by 273. So if you see from this equation that if temperature of like outside is equal to 0 degrees Celsius, then we have 0, like 1 plus 0, square root of 1 is 1. Then we have speed of sound 331 meters per second.
So this is in air, right?
Can you repeat, please?
So this is the speed of sound in air, right?
In air, yeah, exactly.
Thank you.
Yeah, so this is specifically, since we most of the time deal with sound in air, that's quite convenient equation to check temperature dependence of speed of sound in air, but obviously it will be different for different environments. So if we consider 20 degrees Celsius, speed of sound will be something like 343 meters per second. The one interesting option how to estimate distance to some thunderstorm, when you see lighting, you can count seconds, then multiply by like something like this, plus minus 20 degrees of Celsius during summertime and storm, which will give you the speed, the distance to the, so it's like something like 1/3 of a kilometer. 3 seconds is 1 kilometer, so you can estimate distance to the thunderstorm and its moving motion with respect to you if you repeat it several times for different lightnings. Let's say, of course, speed of sound will be higher for more, like higher this mediums with higher bulk modulus and lower density. Different materials provide different conditions for sound propagation. And if we consider, for instance, some solid state materials, then the speed of sound is way higher. For instance, for gold, it is 3,240 meters per second. For aluminum, already twice larger because aluminum is much lighter, 6,420 meters per second. And one of the best material to transfer sound is titanium, which is quite hard and light, kind of unique material. That is 10,253 meters per second. It's beyond 10 kilometers per second in titanium, quite fast. So one more thing we should consider. You remember when we derived the equation for this pressure as a function of position and time. Where is it? No, sorry. Should be here. So yeah, we wrote that maximum change in pressure is B times S maximum displacement times K, which is wave number. So let us write it down here. Delta P maximum equal to B times S maximum times K. So from the expression for the speed of sound, we can write that B is equal to rho times V squared. And also we can write that K is equal to 2 pi divided by lambda. That is, if we multiply it by frequency and divide, it will be 2 pi times frequency divided by lambda times frequency. And that is equal to omega, angular frequency, divided by speed of sound, V. So now if we substitute it here, we can write that delta P maximum is equal to rho times V squared times S maximum times omega divided by V. So V squared and V cancel out, and we can express a relationship between excessive pressure and maximum displacement in terms of density, angular frequency, and speed of sound, which is very nice because it is quite common that density is easier to measure than bulk modules. So, or it's available, so you don't need to find bulk modules. So there is density times speed of sound times angular frequency times maximum displacement of the element of gas from initial position. So during this discussion, we introduced the sound wave. We found the relationship between change in pressure and displacement as a function of position along axis X and time, and managed to derive the equation for the speed of sound, which gives us some universal trend. It's proportional to the elastic properties of the medium and reversely proportional to the inertial properties, in particular density per unit volume, rho. So if you have any questions, you're welcome. Screen. Yeah, so we will continue further our discussion on Wednesday, and that will be one of the key questions we need to discuss is transfer of energy, like intensity of a sound wave, which will be like amount of energy transferred by unit of time per unit area. So that we will continue working with that on Wednesday. And until then, I wish you good evening. Take care, and see you on Wednesday.
Thank you.
Goodbye.
Thank you.
Thank you for the
Bye-bye.
lecture.
Thank you.
Goodbye.
Goodbye.
You're welcome. Bye.